Hello everyone. In this lecture, we will give you an overview of a few selected datasets as your final term project. We select 7 datasets. In week 11, you will study Higgs production as a classification problem and classical two-dimensional Ising model as a classification problem. Next week, there will be 3 datasets. M4Pion is a dataset for energy regression study. Charge particle tracking and digest generative model, these 2 datasets have been studied in previous few weeks. We will study further details and alternative models as your final term project. Finally, there are 2 more datasets. TopJets are used in several examples in previous few weeks. We will prepare a data with comprehensive features to study sophisticated classification problems. The final dataset, electron showers with Imogen detector, is a revised version based on the previous examples. This can be used to study regression and classification problems. In the following, we will present 2 datasets, Higgs production and classical two-dimensional Ising model. The classical two-dimensional Ising model will be presented by Professor Dawei Wang. First, let's start with the Higgs production dataset. It is prepared by Alan based on his recent paper. In this dataset, we pay special attention on high transverse momentum Higgs produced from proton collision in Large Hadron Collider at central mass energy 13 TeV. The Higgs mass used for this study is chosen as 125 GeV mass. The high transverse momentum Higgs could come from the standard model predictions. For example, gluon-gluon fusion is the largest production cross-section at the Large Hadron Collider. The gluon-gluon fusion with a triangle loop of the top quark is the largest production diagrams in the Large Hadron Collider. The same loop here could potentially contribute from beyond standard model particles. This could provide enhancement of the Higgs production. Therefore, a study at the high transverse momentum have a chance to probe the potential heavy beyond standard model particles. This leads to a particular feature. Many Higgs productions other than gluon-gluon edge could be substantial in the boosted region. Boost here means a Lorentz boost, that is the Higgs with high transverse momentum. This diagram shows the differential production cross-section as a function of the transverse momentum of the Higgs. There are 4 curves. The green represents the gluon-gluon fusion process. The red is the vector boson fusion process. Blue is the associated production of the gauge boson V and the standard model Higgs. And the pink is the TT bar associated production with Higgs. The black curve is the sum of all the 4 primary production processes. From this plot, we can learn gluon-gluon fusion is clearly the largest production quotient process. However, when you look at the high transverse momentum up to 1.2 TeV, VH start being compatible with gluon-gluon fusion. The same plot can be viewed through the fractional contribution. This is the contribution of each production process with respect to the total process. Basically, just take the each curve divided by the black curve. From this plot, we can learn greater than 1.2 TeV, VBF star taking over become the most dominant production process. The precision measurement of each production process is a crucial test for the standard model Higgs. In this page, we show the Feynman diagram used for such a physics data set. The gluon-gluon fusions produce the Higgs, while Higgs decay to BB bar final state. The BB bar final state is the largest branching ratio of the Higgs decay. In addition to this process, there's also an initial radiation of a gluon. Therefore, the final state is composed of a gluon with a 2B jets. For vector boson fusion, quark from each of the protons emit gauge bosons. Gauge bosons annihilate into Higgs boson, further decay to BB bar. In this final state, you have 2 light quark with a 2b jet. For vector boson-associated Higgs productions, the vector boson radiate the Higgs boson, which decay to BB bar, and vector boson itself can decay to 2 light quark. The final state will be 2 quark with a 2b jet. In TTH case, the TT bar will be in pair production with the Higgs boson, where Higgs boson decay to BB bar. Top quark can decay to a W boson with a B jet, and W further decay to QQ bar. The TTH process contains largest number of the quarks and the B jets. The goal of the study is to investigate the data set to develop the best classifier to distinguish each of the 4 processes. In the high transverse momentum case, in each of the diagram, a boosted Higgs is contained in the final state. Therefore, the boosted Higgs will not be useful for the event classification. On the other hand, because of the transverse momentum conservation, in each event, the high transverse Higgs will come with the high transverse momentum particles. This gluon and this QQ bar decay from the vector boson, and potentially the quark from the VBF, and also the boosted top could all be high transverse momentum. Based on these kinematic properties, in each event, we expect there will be a boosted Higgs and at least one other high momentum jet. And this leading non-Higgs jet can be used for event classification. Literally, we try to classify a gluon jet from a light quark jet, from a gauge boson jet, and a boosted top jet. The dataset provided here, including high-level features, this is calculated based on the jet mass and jet pseudo-rapidity, the open angle between the 2 leading jets, and the mass of the 2 jets, as well as the angular information of the jet shape. We also provide low-level features, the kinematics of each of the jets, and label of the constituents. There are 35,000 events for each production process for study. In this dataset, we have 4 labels. Gluon fusions labeled 0, vector photon fusion labeled 1, VH process is labeled 2, and finally the TTH process is labeled 3. Here are a few references you might find useful. Some of them also contain the source codes to reproduce the result of the paper.
Today we are going to talk about classical 2D IC model, which is an example for our machine learning. First of all, let me introduce that the IC model is one of the most important model discussed in condensed matter physics because it is the simplest non-trivial model with exact solution available in 1D and 2D systems. Okay, and the 2D case also shows a phase transition in thermodynamic limits. So in order to understand how it works, so let's see the general many-body Hamiltonian. So it is composed by 2 terms. One is the spin coupling term J, where the spin is just polarized in Z direction, spin up, spin down. Okay, and there's in general a transverse magnetic field, which is polarized in X directions. And then here sigma X, Y, Z are polymetrics at a certain lattice site. Okay, and here the IJ, the pair of IJ means that it is nearest neighbor pairing sites. Okay, but now this is a quantum mechanics version of IC model. But in our case, we emphasize classical limits, which means that first of all, we take zero magnetic field, and also because when it is zero magnetic field, then all the spin operator commute with each other. So the eigenstate could be will be just spin up or spin down for different kinds of spin configuration at each side, right? So therefore, for this kind of spin configuration, we can replace this Hamiltonian by simply the total energy for given spin configurations. So now sigma z is just plus 1 or -1, okay, for each side. So it's just a C number. And from here, we could also calculate the average magnetization. And from this energy, so at finite temperature, what we should do is to calculate the partition functions. And from this partition function, take the derivative with respect to magnetic field, and we can get so-called magnetizations at finite temperature. So it is just some kind of ensemble average of this magnetization. So this is the very fundamental physics we know, but there could be a very important consequence for this model. The most important consequence is that in two-dimensional case, it is known that it will have a finite temperature phase transition in thermodynamic limits, which means that when temperature, so here example, there's an exact solution, solid line is an exact solution. When temperature is above some Tc, the magnetization is from finite drop to 0. Okay, and so in this large temperature region, we call it paramagnetic phase. In the lower temperature region, we call it ferromagnetic case. But before going to thermodynamic limits, the lattice side from small to large, you can see that it changed gradually to sharp discontinued ones. Okay, but of course, for any finite size, the phase transition is not discontinuous, but that's what we expect and could be proved analytically in thermodynamic limits. So for our machine learning problems, what we will have is that we have a lot of spin configurations. For example, like here, for we have different number of sites. For each side, we use black and white to be like a spin up or down. So when temperature is larger than Tc, so it's a paramagnetic phase, means that there's no preferred spin directions. But when temperature is below Tc, there could be a symmetry breaking, which shows that a certain more spin up, for example, because their spin exchange coupling preferred to make the spin parallel to each other. So it forms a domain. But around Tc, you can see that the domain becomes fractionized, so that it can looks like some domain, but not really. And there are a lot of fractal patterns therein. So in our calculations, basically you can use supervised learning to train a configuration, to train a model which can recognize a configuration in lower temperature and recognize a pattern in higher temperature, and try to use supervised learning to determine that if we could identify the critical temperature. Or you can use unsupervised learning to cluster this spin configuration and see if you can classify them into two groups and decide where is the Tc. Okay, so the data structure is following. For X data, okay, so it has 10 by 10 system size with periodic boundary conditions, and use 1 or -1 to represent the spin up down. And also it has more than 1,000 temperature in a wide temperature range. And also I will also tell you what is the critical temperature. And for each temperature, there are 100 ensembles, so that you can use this to do machine learning. For the label data, so basically we have a one hot label to show if it is paramagnetic or ferromagnetic. Okay, so you can use this data to do supervised learning. Okay, so that's all, and hope it is helpful.